In this module, you will learn to solve linear programming problems. Let us recall the graphical solution of a linear inequality. Given a linear inequality, x plus y less than 6, its solution can be found graphically by first drawing the graph of the equation x plus y is equal to 6, and then consider an arbitrary point that is not on the line. For example, the origin, if it satisfies the linear inequality. Then the solution region is towards the origin, else it is to the other side of the line. To find the solution of the system of linear inequalities, we draw the graphs of the inequalities in the same manner and find the common region. The common region of the solution of the inequalities is the solution of the system. Now, let us apply the graphical method of linear inequalities to solve linear programming problems. Let's take a look at one problem. In this problem, a manufacturer produces two different models of a product and wishes to maximize his profit under some given conditions. Such type of problems, which seek to maximize or minimize profit on cost, form a general class of problems called optimization problems. The special type of optimization problems is linear programming problems. Linear programming problems involve the optimization of a profit or cost subject to certain overriding conditions or constraints. There are several methods to solve a linear programming problem, but in this chapter, we will learn only the graphical method. Let us now frame the inequalities in terms of x and y. In this problem, the number of units cannot be negative. Hence, x and y are greater than or equal to 0. Machine 1 takes 1 hour to complete 1 unit of model A and 4 hours to complete 1 unit of model B. Therefore, the time taken by machine 1 to make 1 unit of both the models is equal to 1 into x plus 4 into y hours. Now, machine 1 can work for a maximum of 8 hours. Therefore, the linear constraint is x plus 4y is less than or equal to 8. Given that the second machine is used for 2 hours to complete 1 unit of model A and 2 hours to complete 1 unit of model B, and it cannot be used for more than 10 hours, it implies that 2x plus 2y is less than or equal to 10. This can be simplified to x plus y is less than or equal to 5. It is given that the profit on model A is rupees 100 and on model B is rupees 200. And hence, the total profit is 100x plus 200y. This is the objective function. The manufacturer wants to earn the maximum possible profit. This can be attained by maximizing the objective function. Mathematically, a linear function z is equal to ax plus by, where a, b are constants and which has to be maximized or minimized, subject to constraints in the form of linear inequalities, is called a linear objective function. Let us now solve the linear programming problem using graph. Obviously, x greater than or equal to 0 and y greater than or equal to 0 have the solution in the first quadrant. the solution of the inequality x plus 4y is less than or equal to 8 is the shaded region as shown. The solution of the inequality x plus y is less than or equal to 5 is towards the origin. The common region of all these inequalities is known as the feasible region or feasible solution. To maximize or minimize the objective function, we use two theorems. The first theorem is, if R is the feasible region for a linear programming problem and Z is the objective function, then the maximum value or minimum value of the objective function must occur at the corner point of the feasible region when it is a closed or bounded region. The second theorem is, if the feasible region is open or unbounded, then the maximum or minimum value of the objective function may not exist. If it exists, it occurs at a corner point of R. When the feasible region is closed, let P and Q be the maximum and the minimum values of the objective function. If the feasible region is open, we have two cases. Case 1. If the open half plane determined by ax plus by greater than P has no point in common with the feasible region, then P is the maximum value of the objective function. Else, there is no maximum value. If the open half plane determined by ax plus by is less than Q has no point in common with the feasible region, then Q is the minimum value of the objective function. Else, there is no minimum value. This method of finding the maximum or minimum value of an objective function is known as the corner point method. Let's come back to the problem that we were discussing. Here, the feasible region is a closed region. The corner points are O, 0, 0, A, 5, 0, B, 4, 1, and C, 0, 2. As per Theorem 1, the objective should be maximized using the corner points of the shaded region. Let us substitute the corner points in the objective function. The value of the objective function is 0 at the origin, 500 at A, 5, 0, 600 at B, 4, 1, and 400 at C, 0, 2. The maximum value of the objective function is 600, which occurs at B, 4, 1. Hence, 4 units of model A and 1 unit of model B should be made so that the profit is maximum. In this module, you will learn to apply linear programming to solve problems of manufacturing type. In the previous lesson, you learned to solve some special class of optimization problems called linear programming problems. Now, let us learn the manufacturing type of linear programming problems. Manufacturing problems are helpful in determining the number of units of different products that should be produced or sold by a firm when each product requires a fixed manpower, machine hours, labor hour per unit of product, warehouse space per unit of the output, etc., in order to make maximum profit. Let us take one example of this type. A box manufacturer makes small and large boxes from a large piece of cardboard. The large boxes require 4 square feet of cardboard per box, while the small boxes require 3 square feet of cardboard per box. The manufacturer is required to make at least 3 large boxes and at least twice as many small boxes as large boxes. If 60 square feet of the cardboard is in stock, and if the profits on the large and small boxes are 3 rupees and 2 rupees respectively, how many of each should be made in order to maximize the total profit? Let us start with the solution now. Let X and Y be the number of small and large boxes respectively. This implies that X and Y are greater than or equal to 0. It is given that each small and large box requires 3 square feet and 4 square feet of cardboard respectively. Therefore, the total cardboard required is 3x plus 4y square feet. 3x plus 4y should not exceed 60 square feet, as the cardboard available is only 60 square feet. One more condition is that at least 3 large boxes should be made. It is also given that the number of small boxes is at least twice as that of large boxes. The profit on one small box is 2 rupees, and on one large box is 3 rupees. Hence, the total profit is rupees 2x plus 3y. Therefore, the objective function z is 2x plus 3y. As we need to find the maximum profit, the objective function should be maximized using linear inequalities. Let us now draw the graphs of the inequalities, treating them as equalities. Obviously, x greater than or equal to 0 and y greater than or equal to 0 have the solution in the first quadrant. Let us draw the graph of 3x plus 4y is equal to 60 as the reference to get the solution region of the inequality towards the origin. Draw the graph of x is equal to 2y as the reference to get the solution region of the inequality as shown. Y is equal to 3 is the line that is parallel to the x-axis and intersects the y-axis at 0, 3 as shown. The common region of the inequalities 1 to 4 is the feasible region as shown. The coordinates of the corner points of the feasible region are A, 6, 3, B, 12, 6, and C, 16, 3. Let us substitute the corner points in the objective function. The value of the objective function is 21 at A, 6, 3. Similarly, the value of the objective function is 42 and 41 at the points B, 12, 6, and C, 16, 3, respectively. The maximum value of the objective function is 42, which occurs at B, 12, 6. Thus, to get the maximum profit, 12 small boxes and 6 large boxes should be made. In this module, you will learn to solve diet problems based on linear programming. Recall that in manufacturing type problems of linear programming, we determine the number of units of different products that should be produced and sold by a firm when each product requires a fixed manpower, machine and labor hours per unit, etc., in order to make maximum profit. Let us now learn to solve diet problems, which is also a type of linear programming problem. In these problems, we determine the amount of different kinds of nutrients and the constituents that should be included in a diet, such that the cost of the diet is minimum and it contains a certain minimum amount of each constituent or nutrient. Let us see a problem of this type. A housewife wishes to mix together two kinds of food, P and Q, in such a way that the mixture contains at least 10 units of vitamin A, 12 units of vitamin B, and 8 units of vitamin C. The vitamin content in units of 1 kg of food P and food Q is shown in the table. 1 kilogram of food P costs 6 rupees and 1 kilogram of food Q costs 10 rupees. Find the minimum cost of the mixture that will produce the diet. Let us start the solution now. Let X kilograms of food P and Y kilograms of food Q be mixed together. This implies that X and Y are greater than or equal to 0. 1 unit of vitamin A is present in food P and 2 units in food Q. The total content of vitamin A is X plus 2Y. However, the mixture has to contain at least 10 units of vitamin A. This implies X plus 2Y is greater than or equal to 10. 2 units of vitamin B are present in food P and 2 units in food Q. The total content of vitamin B is 2X plus 2Y. However, the mixture has to contain at least 12 units of vitamin B. This implies 2X plus 2Y is greater than or equal to 12, or X plus Y is greater than or equal to 6. Similarly, 3 units of vitamin C are present in food P and 1 unit in food Q. The total content of vitamin C is 3X plus Y. However, the mixture has to contain at least 8 units of vitamin C. Thus, 3X plus Y is greater than or equal to 8. 1 kilogram of food P costs 6 rupees and 1 kilogram of food Q costs 10 rupees. The cost of X kilograms of food P is 6X rupees, and the cost of Y kilograms of food Q is 10Y rupees. Therefore, the total cost of food P and food Q is 6X plus 10Y. This is the objective function. To find the minimum cost of the mixture, the objective function should be minimized using the given constraints. Let us draw the graphs of the inequalities, treating them as equalities. Obviously, X greater than or equal to 0 and Y greater than or equal to 0 have the solution in the first quadrant. Draw the graph of X plus 2Y is equal to 10 as the reference to find the solution of the inequality. Draw the graph of equation X plus Y is equal to 6 as the reference to get the solution region of inequality. Finally, draw the graph of 3X plus Y is equal to 8 as the reference to get the solution of the inequality. The feasible region of the inequalities 1 to 4 is open or unbounded region. The coordinates of the corner points of the feasible region are A 10, 0, B 2, 4, C 1, 5, and D 0, 8. Let us substitute the corner points in the objective function. The value of the objective function is 60 at A, 10, 0. Similarly, the value of the objective function is 52, 56, and 80 at points B, 2, 4, C, 1, 5, and D. 0,8, respectively. The minimum value of the objective function is 52, which occurs at b 2,4. Since the feasible region is unbounded, we need to draw the graph of the inequality 6x plus 10y less than 52. On simplification, this gives 3x plus 5y is less than 26. Observe that there is no common point between the feasible region and the open half plane of this inequality. Clearly, the minimum value of z is 52, attained at the point 2,4. Hence, the minimum cost of the diet is 52 rupees when 2 kilograms of food P and 4 kilograms of food Q are mixed. In this module, you will learn to solve transportation problems using linear programming. In the previous modules, we learned to solve manufacturing problems and diet problems of linear programming. Let us now learn one more type of linear programming problems called transportation problems. In these problems, the transportation schedule is determined in order to find a way of transporting a product from factories situated at different locations to different marketplaces at the minimum cost. Let's take up one example. An aeroplane can carry a maximum of 200 passengers. A profit of 400 rupees is made on each executive class ticket and 300 rupees on each economy class ticket. The airline reserves at least 20 seats for executive class. However, at least 4 times as many passengers prefer to travel by economy class than by executive class. Determine how many tickets of each type must be sold in order to maximize the profit for the airline. Also, what is the maximum profit? Let the number of tickets of executive class and economy class be x and y respectively. Hence, x and y are greater than or equal to 0. The maximum number of passengers in the plane is 200. Hence, x plus y is less than or equal to 200. The airline reserves at least 20 seats for executive class. It implies that x is greater than or equal to 20. However, at least 4 times as many passengers prefer to travel by economy class than by executive class. This gives us the inequality y is greater than or equal to 4x. It is given that a profit of 400 rupees is made on each executive class ticket and 300 rupees on each economy class ticket. The total profit is 400x plus 300y. Hence, the objective function is z is equal to 400x plus 300y. To find the maximum profit, the objective function should be maximized using the constraints 1 to 4. Let us draw the graphs of the inequalities, treating them as equalities. The solution set of x is greater than or equal to 0, and y is greater than or equal to 0, is represented by the first quadrant. Draw the graph of x plus y is equal to 200 as the reference to get the solution of the inequality. Draw the graph of y is equal to 4x as the reference to get the solution of the inequality. Draw the graph of x is equal to 20 as the reference to get the solution of the inequality. The feasible region of the inequalities 1 to 4 is a bounded region. The coordinates of the corner points of the feasible region are a 20, 80, B 40, 160 and C 20, 180. Let us substitute the corner points in the objective function. The value of objective function is 32,000 at 20, 80. The value at 40, 160 is 64,000 and its value is 62,000 at 20, 180. The maximum value of the objective function is 64,000, which occurs at B 40, 160. Hence, 40 tickets of executive class and 160 tickets of economy class should be sold to get the maximum profit of 64,000 rupees. Let us solve one more transportation problem now. A factory is located at two places, P and Q each. From these locations, a certain commodity is delivered to each depot situated at A, B and C. The weekly requirements of depots A, B and C are 5, 5 and 4 units, respectively, while the production capacities of the factories at P and Q are 8 and 6 units, respectively. The cost of transportation per unit is shown in the table. How many units should be transported from each factory to each depot in order that the transportation cost is minimum? Let us solve the problem now. Let X be the number of units transported from P to A, and Y be the number of units transported from P to B. Let us place the values in the table now. Now, X number of units are transported from P to A, and Y number of units are transported from P to B. Therefore, the number of units still left at P is 8 minus of X plus Y, which are to be transported to C. As the requirement at depot A is only 5 units, the number of units sent from Q to A is 5 minus X. Similarly, the requirement at depot B is only 5. Hence, the number of units sent from Q to B is 5 minus Y. The number of units left in depot Q is X plus Y minus 4. Let us form the inequalities using the data in the table. The inequalities are X greater than or equal to 0, Y is greater than or equal to 0, X is less than or equal to 5, Y is less than or equal to 5, X plus Y is less than or equal to 8, and X plus Y greater than or equal to 4. Using the table for cost and the number of units, and simplifying, we get total cost of transportation as X minus 7Y plus 190. To find the minimum cost of the transportation, we need to minimize the objective function Z, which is equal to X minus 7Y plus 190. Let us draw the graphs of the inequalities, treating them as equalities. Obviously, X is greater than or equal to 0, and Y is greater than or equal to 0 have the solution in the first quadrant. Draw the graph of x plus y is equal to 8 as the reference to get the solution of the given inequality. Draw the graph of x plus y is equal to 4 as the reference to get the solution of the given inequality. Draw the graph of x is equal to 5 as the reference to get the solution of the inequality. Draw the graph of y is equal to 5 as the reference to show the solution of the inequality. The feasible region of the inequalities 1 to 5 is a bounded or a closed region. The coordinates of the corner points of the feasible region are a. 4, 0, b. 5, 0, c. 5, 3, d. 3, 5, e. 0, 5, and f. 0, 4. Let us substitute the corner points in the objective function. The value of objective function is 194, 195, 174, 158, 155, and 162 at the points 4, 0, 5, 0, 5, 3, 3, 5, 0, 5, and 0, 4 respectively. The minimum value of the objective function is 155, which occurs at e 0, 5. The values of x and y are 0 and 5 respectively. Substituting the values of x and y in the table, we get the required number of units to be transported from P and Q to A, B and C. So from the factory at P, we must transport 5 units to depot B and 3 to depot C, but none to depot A. Similarly, from the factory at Q, we must transport 5 units to depot A and 1 unit to depot C, but none to depot B. This will keep the transportation cost to the minimum.